quickly. So today's already the last day, other than examination and other formalities tomorrow. And we've got a pretty packed day. And I can relieve you that the last lecture that we'll be doing, it will be more so... there's the tea already. Thank you. We'll be more so working towards the preparation of how we're going to do the exam. I think some of you have ordered this to get me to slow down talking. allowed even a break to go to the toilet. Just joking, we will take some breaks in the middle. And if you need a break because you feel you're getting all tired, please let me know. We can break quickly so that everybody can stretch their legs, because 3 hours talking without breaks is just too long. In Australia, lectures are only 50 minutes.
It's going to be very hard for you rather than for us.
Certainly the first one, I'll be talking about functional integration by digital light projection. That's all my own work, so that's easy to talk about. Later in the day, I'll get to a lot harder things, because I've tailored it a little bit to making nanoparticles and aggregate, and the areas as well as organometry, and they're all areas that I'm not familiar with. We'll get there. So the work that I'll be talking about, I had a really, really good student, Harry, and he's getting married in 2 weeks' time, and he invited me to go to the wedding. So I'll be attending my first Indian wedding ever, which I'm really looking to. But Harry was an excellent PhD student, mechanical engineer by background, and managed to the chemistry reaction and did really well. So he's now doing a postdoc in Abu Dhabi and working very closely with the industry. Has some IP that's about to be licensed, so he's doing well. So what we'll be talking about is multi-material digital light projection in presence of a porogen. We found out that the chemistry that is used for digital light projection 3D printing, it is just an acrylate chemistry. And in a previous life, I had worked with the synthesis of polymer monoliths. At that stage, that was really a hot topic to make columns for liquid chromatography. And one of the reasons they were so attractive for HPLC is because even in nanobore columns, they had a very low flow resistance. We then took the same approach of taking a highly porous, low flow resistance scaffold, but then use it for heterogeneous catalysis. So we functionalized the polymer monolith, put a ligand on top with some palladium, and then we're able to do palladium in these flow-through microreactors. Moving then years later into the digital light projection, I'm like, I've seen this chemistry before, I know this. And at the same time, we had the need to start making porous membranes. Because we like functionality. The first step in sample preparation quite often is removal of particulate matter. And porous materials then are the first thing that jump to mind. So the idea was, could we adopt the chemistry that we use for making the porous materials to do either heterogeneous catalysis or separations on? Could we use the same chemistry, that same concept, in 3D printing? And the answer there was yes. And what we realized, that there were two different areas that we could play with in creating the fine-tuning the material properties. One was with the resin chemistry. What is the monomer or monomers that you're using? What is the porogen, or typically porogens, the solvents that are not participating in the reaction, but take space and therefore create voids that are ultimately leading to the porosity? What is the role of the photoinitiator and the photoabsorber in this effect, and how can we, so they are the chemical ways of fine-tuning the porosity. And there are the printer settings, which are the exposure time, the light intensity, the layer number, and the layer height. So throughout Harry's work, he explored these different parameters and then applied it to some different applications, going one step at a time. So the first test was, can we actually, by adding a porogen to a normal 3D printing resin, can we make a porous material? And we did that with two sets of monomers. We tried that with hydrophilic monomers. PEC is, as we did yesterday, with the digital light projection. We added, in this case, methanol, and we found that actually we indeed could create flat sheet membranes when we designed them to be. They had a thickness of about 200 micron, We also could print them 100 micron, but we couldn't get them off the pick. So the pick is the metal plate that it's sitting on at the moment. So we needed to have a two-layer print to get the structural rigidity so that we actually could take it to our equipment for characterization. But we So we created a little flow cell to see if the membranes actually could be used for filtration. Here we've got a setup where we've got a sample, an input coming in, which was a suspension of some microparticles in water. We have a flow of water coming out that goes from the top of the membrane, and we've got the bottom of the membrane. And you can see the permeate, the solution that has gone through the membrane, doesn't contain any particles, whereas the retentate, the liquid that hasn't passed through the membrane, but has flown out, contained all our particles. So we were able to separate, filter out particles, and end up with a particle-free solution using our 3D printed flat membrane.
Characterization was done through?
Just microscope and counting the beads.
Okay.
So collect the permeate, collect the retentate, place a droplet of that solution on a microscope slide, and look under the microscope to see in a grid. You can see particles, and then you can calculate back to how many particles there were. So here we use the fluorinated monomer, which has got a funky name. Use cyclohexanol as a porogen, because one of the important things about the porogens is they need to be the monomer and porogen need to be miscible. So we use cyclohexanol, which mixed well with the F13F001, and then 3D printed the porous membrane. Here we can see the droplets beading up. The contact angle is 148 degrees, which we are still sad about, because materials are considered super hydrophobic if the contact angle is over 150 degrees. So it is nearly super hydrophobic, but we couldn't get it to cross that barrier. So we just still have to only refer to it as a hydrophobic system. What we did here is to print the device with a print pulse print approach that we already talked about. So here in black we printed the flow cell. We changed the resin formulation to this one. We printed the two layers to have our 200 micron thick membrane. In the design there was a little spacing left in the first layer for the membrane to fit in. And then we continued with the print so that we could get an enclosed fluidic flow cell, fully made by 3D printing, that we just had the fittings to attach the tubing to and could use for separation science. So we tried a couple of different compositions of this material. We found that if we decrease the amount of porogen, we decrease our pore diameter. It was even only 143. And we could see that if the more porogen we had in there, the more hydrophobic our material became. But yeah,
How this characterization was done?
A perimeter. So it is an instrument that applies increased pressure and then measures the flux through the membrane, and does that with fluorinated solvent first under wetted conditions and then with nitrogen.
What's the name of the equipment?
Porimeter.
Porimeter.
So it is a standard piece of equipment used to measure the pore size in membranes. So there's two different ways of doing that. There is mercury intrusion perimetry, and that measures all the pores, also the ones that don't go from one side to another. So it increases the pressure and looks at the volume of mercury that you can squeeze into the pores.
Okay.
Whereas the perimeter applies pressure over the membrane and measures at what pressure how much flux gets through the pores. So the difference between the two pore sizes is one has got overall porosity, having the sum of the pores that go through the material and the ones that are just dead end streets.
Okay.
And in this way you measure the pores that allow that support any flux. So we use this for phase separation. So we had, in this instance, we had a two-component mixture existing of ethyl acetate and water that are non-miscible. We used a simple T-piece to create droplets. In this instance, we again use Teflon tubing. Teflon is hydrophobic, so which becomes the continuous phase, the water or the ethyl acetate?
Water?
No, we've got a hydrophobic tube. The hydrophobic tube prefers to be wetted by the solvent over water. And the continuous phase is always the one that wets the surface.
Then it will be.
Yeah. So our water is our dispersed phase.
Okay.
So we've got blue droplets and the ethyl acetate is our continuous phase. So we connect to a dual syringe pump, a T-piece, create the droplets. Droplets were introduced into the membrane. The hydrophobic membrane would have passed the aqueous or the organic phase.
Organic?
Organic. So the ethyl acetate would pass through the membrane, whereas the aqueous phase, the pressure was too high to pass through the membrane and would come out. So we could phase separate the water and the ethyl acetate using the hydrophobic membrane, where our permeate contained our organic phase, the ethyl acetate, whereas our retentate was the water, because the pressure to allow the water to move through was too high. So we had to balance the pressure a little bit, where at some if there's no back pressure applied at all, we didn't get any separation. Initially we got still a little bit of ethyl acetate coming out in our retentate. And then after optimizing the pressure coming in from one side and being pushed back from the other, we managed to get the right pressure across our membrane that allowed all of our ethyl acetate to go through and have no water in the permeate, no ethyl acetate in the retentate. So it was a little bit of trial and error, and he can look at a couple of different pressures where we changed the back pressure and looked at what the flow rate was coming out and how clean that was. So we defined some optimal ranges where we could use this flow cell for the phase separation of water and ethyl acetate.
Here the equipment used was?
We had flow sensors, so the pressures were measured with pressure sensors that we put in the reservoirs. The flow was measured with a flow sensor that we bought online. So there are pressure controllers that you can buy with little flow sensors.
So then plotting was done in the Excel and all?
Yeah. So with the idea of doing functional integration, we looked at optimizing the chemistry and creating, if you remember us yesterday talking about the size mobility trap, the next application that we worked on was trying to see if we could create a size mobility trap with two different porosity membranes, knowing that through optimization of the resin chemistry, we could create different porosity membranes. So this is the device that we tried to develop. We have two different reservoirs, or three different reservoirs. We've got two large reservoirs, one to contain a sample, thermal lysate of E. coli, one to contain buffer, and one to contain our extract. We would like to concentrate the sample, extracting it from our sample reservoir. We would like to concentrate our analyte into a small volume. Therefore, the sample collection chamber here was designed to be really small. We looked at the resin composition to see how we could tune the pore size. And what we found that if we want to have a significant, like an order of magnitude difference in pore size, doing that with the photoinitiator concentration is really difficult. You can go from like 200-300 nanometers to 700-800 nanometers, but not really an order of magnitude in size. But if you start manipulating the porogen, you can actually get significant changes in pore size. So we created 2 different membranes in the print process. For one membrane, we used 70% porogen. So we had a PECDA resin with 70% methanol in there. We created a membrane with large pores, from memory somewhere around 300 nanometers on one side. Then we cut down the porogen concentration to 50% and printed the other membrane with that. And that membrane had pore sizes we could no longer measure, but still allowed us to carry a current. And therefore we assumed there would be some transport of small inorganic ions coming through. Because if we took any less porogen, we could no longer measure a current. So we don't exactly know the pore size because the perimeter said it's non-porous, but we could still measure electrical conductivity, which automatically means that there's transport of electrons and small inorganics. So we made this device by print pros print. So we printed the bottom yellow part, first reservoir, paused, exchanged for the resin containing 70% methanol, created membrane number 1, got back to the original resin, printed a small analyte extraction reservoir, exchanged resin to our narrow pore size membrane, printed that membrane, and then exchanged back to our resin that didn't contain any porogen, and printed the rest of the device. So the macroporous membrane separates number 2, which was the extraction chamber, and had a pore size about 300 nanometers. So aims here that DNA could be electroextracted across this membrane, but proteins and cell debris wouldn't. Our other pore size was, our best approximation is around 20 nanometers. We would like to this membrane to stop the migration of DNA, but still allow sodium and chloride to get through to carry our current and establish our electric fields. As already said, the bottom of the extraction chamber here, chamber 2, was really shallow to minimize the volume and to enhance the concentration enhancement factor that we could realize using our electroextraction. We've optimized that resin exposure. Let's see. Okay, so we looked at the different properties, how we could influence the porous properties of the material. So if the exposure time per layer is reduced, here we go from 120 seconds to 30 seconds, we can see an increase in our pore size and also a broadening of our pore size distribution. The density of our resin decreases as well, and we get a decreased strength and lower breathability if we really want to get any smaller pore sizes. So we like the smallest pore size there that we had. Then we looked at the chemistry, we looked at the photoinitiator concentration. If the photoinitiator concentration increases from 1% to 4%, again 1% here, we can see the more photoinitiator, the smaller the pore size. Our target, we thought, for allowing DNA and not stop the proteins was around 500 micron. So we selected that the composition with 3% porogen to create our first membrane. And here you can see some SEMs of the materials as they form. And you can see if you've ever seen SEMs of polymer monoliths used in HPLC, it is the same cauliflower-like structures that are evident of the fact that during photopolymerization, we get the growth of our polymer chains, and at a certain point these polymer chains phase separate and crash out of solution and form a solid. And that typically is a process that works in these mesoporous flower-like structures. Really, really beautiful to look under in an SEM. So we then, indeed, as I already said, looked at the amount of porogen. At 50%, we think the pore size was around 20 nanometers, and we had a current. When we dropped the porogen content further down to 45%, there was no more current, and we couldn't measure a pore size either. So that was all the work that was done by Harry, one of my students, but he was a mechanical engineer and doing DNA amplification teaching, and that seemed to be a step too far. Luckily, I had another really nice student in my group, which is Sumin Lee, and her PhD was on simplifying the chemistry for lysis and DNA extraction. And for all the work that she did, she had to validate all the results with PCR. So we called in the help of Sumin to look at the extract that Harry had, and Sumin put it into the PCR and then helped conducting the analysis to quantify the DNA coming out. So what we did in the essay was that we pipetted the E. coli lysate into our sample reservoir. We applied a potential difference. DNA is negatively charged, so it will migrate towards the positive electrode. First membrane was the one with the 300 nanometer pores, so the DNA would have no problem passing that first pore. Then we had a pore-sized membrane, and the DNA didn't fit through, which means that even though there was a driving force of the DNA to go to the TBE buffer reservoir, it couldn't pass through. Yet we still had a large buffer reservoir here to provide us with significant buffering capacity. Because one of the things we realized that when we had our electrode in the same reservoir as our extract, we got so much H plus being formed that we significantly changed the pH of our solution, which then interfered with our amplification. So having a large reservoir here was purely there to provide us with the buffer capacity to absorb all the proteins being formed due to electrolysis as a result of the application of an electric field over our extraction cell. Our E. coli lysate was in buffer as well, so the hydroxides generated there would be comfortably mopped up as well. Here are the results, and one of the things with PCR is what you measure is the CQ value, which is the number of times that you need to thermocycle to get a certain threshold value. If you start off with a high concentration of DNA, that means that you don't need to go through a lot of cycles to get over your threshold. So a low CQ value means that you had a lot of DNA in your sample. The more cycles you need to amplify your DNA, the lower the start concentration was, because that is the number of cycles that you need to go over the threshold. So a high value in this graph means there was very little DNA to amplify. A low value means there was a lot of DNA to amplify. So that's a little bit the opposite to analytical chemistry, because things like absorption, high is always better. With PCR, low is always better. It takes a little bit of rethinking. The other thing about the CQ value, because DNA is a logarithmic process, an increase in CQ value actually means a factor of 10 more DNA. So whereas the numbers go up linearly, please be aware there's a significant difference between a CQ value of 20 or 20 to 23 in the amount of DNA that is present. So we optimized the DNA extraction on two different parameters. First, we looked at the potential difference applied across the cell. So we increased the potential difference from 2.5 volts to 15 volts. And we saw that we got a decrease in CQ value, so an increase in DNA in our extract when we increased our potential difference. The other parameter that we looked at was increasing the time. So we did this for 5, 10, 15 and 20 minutes. And we could see that we got a decrease in CQ value, So also an increase in DNA concentration if we extract it for longer. No big surprises there. If you have a higher potential difference, you get a higher number of ions moving, so you extract more DNA. If you do that for longer, you get more as well. But we still found that there was an optimum, because above 12.5 volts, we got serious problems with the electroosmotic flow, and we started seeing significant differences in liquid height in our reservoirs, because we were pumping our liquid from one reservoir to another. The other thing that we saw, that after about 20 minutes, our devices were uncovered. We actually lost a lot of our water due to evaporation. So we said no more than 12.5 volts. Let's stick with the 15 minutes, because we get increased error bars and no real significant gains anymore, because we get evaporation and then we get big changes from one day to another. So under optimum conditions, the CQ value ended up just over 17. We then looked at the recovery rate of both the DNA and the protein. And we found that we could remove 73% of the protein. So we did that using a nanodrop instrument. And we could see that our recovery rate went close to 95% at the 15 minutes.
Which instrument? Nanodrop?
The nanodrop. So the nanodrop is an instrument that measures the ratio in absorption over, I think it is 260/380. So it gives you the ratio protein to DNA in a solution, in a small droplet. So it gives you a ratio of absorption at two different wavelengths, okay, which is one of the analytical approaches that molecular biologists use to test if they've removed enough protein and have sufficient DNA to start amplification, or if they need to dilute. So we looked at the relative extraction efficiency over time, and we could see that again under our optimized conditions, we were over 90% efficiency. And a commercial kit that we could buy off the shelf that most molecular biologists use to extract their DNA was 93.7. So we were not significantly different in our extraction efficiency compared to commercial kits. We looked at the CQ value when we had increasing amounts of E. coli in there, and here you can see that over a concentration range, if the concentration of E. coli increased, we could see a nice decrease in our CQ value. So we had a quantitative test there with the PCR to quantify E. coli in the lysate. So in principle, this could be used for the detection of E. coli in a range of different samples. The next application that we tried to use for our membrane integrated devices was for chemotaxis. So for those of you that are doing any biological projects, chemotaxis is the process that microorganisms, but perhaps people, are also attracted to certain chemical cues. So if you're hungry and you walk past a bakery and you smell freshly baked goods, you want to go there. Microorganisms do exactly the same thing. If they smell a food source, they want to go there. If they smell something that's bad for them, they don't want to go there. And we looked at chemotaxis with little zebrafish embryos, as well as planarians. Planarians are little worm-like creatures that are present in lakes. So chemotaxis is directional. If you really want to go somewhere, if it really smells good, you go there. If it really smells bad, you move in the other direction. Whereas chemokinesis is just a movement in random direction. So we developed a little test device about the size of a microscope slide, where we wanted to look at the role of a chemical gradient to different microorganisms. So we have the bulk of the device here. We again used print, pore, sprint, and we integrated two different membranes with a pore size of around 400 micron. The reason that we needed a membrane is that we knew that the planaria really liked a liver extract. A liver extract contains a lot of cells and debris, and if you want to study your planarians in presence of the liver extract, you can't see your planarians anymore because your solution is too dirty. So here our plan was that we would have a solution or a reservoir that we could pipette our liver extract in. Our molecular components would be diffusing through the membrane and establish a concentration gradient in the flow cell. The planarians would really like the chemotractants, they would swim that way. If they didn't care, they would equally distribute. If they would really hate the liver, they would all be sitting at the other side. So we printed the device again using the print pause print approach, where we print the first part of the device, change the resin, print the membrane, and then print the remainder of the device. And then the second one gets printed. So here you can see some SEMs that still we have this cauliflower-like material. We control the membrane properties here by looking at the exposure time using the layer thickness. So here we can see that we set our printer layer thickness at 200, 150 or 100 micron, and could see that the thicker our layer thickness was, the longer the exposure time, the higher the light dose, and therefore the smaller the pores of our membrane. And again, these observations agreed with a decrease in porosity and an increase in density of the porous materials that we formed. We found out that we got the narrowest pore size distribution, as well as the best, the lowest amount of breakages in our membrane if our membranes were composed of 300 micron thick layers. So we took the layer of 100 micron, but then repeated 3 layers, which tightened down the pore size a little bit as well. Once we had the devices, we started looking at what a small molecule would do and how long it would take to establish concentration gradients. So here you can see a couple of devices in the setup. I think it's nice to see here that there's no rocket science in the way that we do our experiments. We've got a Petri dish here, a desk light, some graded paper so that we can, from our photographs, derive distances. And we had a stopwatch to measure time. We filled a fluorescing solution into the top component, and we waited for increasing numbers of time, and we could see indeed a fluorescing front progressing through the membrane to the other side. So we knew that over time a concentration gradient would establish, and could anticipate that if this is for a small molecule, around 400 daltons is fluorescing, proteins will take a little bit longer, small inorganics would take a little bit shorter. So after 15 minutes, we could see the first fluorescence showing up in the chamber. So it would take a little while for a visible amount of fluorescence to actually have migrated through the membrane. About 30 to 40 minutes, small molecules are halfway, and after an hour, the whole chamber has got kind of a homogeneous concentration, and we wouldn't be able to really study chemotaxis behavior anymore. So with this, we limited our operation behavior for the experiments to a period of 45 minutes. So here we've got the experiment done with little zebrafish. Zebrafish get a little bit scared if you handle them. So we had a device ready with our sample not introduced yet. Put a little cylinder there so that the zebrafish were no longer stressed by the time that we started the experiment. At T is 0, we could lift out this little cylinder, and the zebrafish could start swimming in any direction they liked. And if you see the green dots are the zebrafish that we could count at the chemotractant site. The red ones are the ones that we found at the water site. And you can see that the time that each of the zebrafish spent at the chemotractant site was significantly higher than they spent at the bottom of the device. Here the heat map perhaps shows it a little bit better even, where blue means there's hardly any time of the zebrafish spent. Red means that they're around there all the time. So the zebrafish were all the time looking for nutrients in the top part of the device. It's the same thing then with our planaria, with our liver extract.
What's the green and the red.
It is a color scale for visualizing, so it's a heat map. And in the heat map you can define the frequency of visits. So blue means that we've got very few visits, red means that we've got a lot of visits. So we created a heat, so we determined the location of the planarian and then gave a color value to each of the frequencies, and that then allows you to visualize it in the form of a heat map. So it is a way of plotting your data when it becomes multidimensional and you can't just have a calibration curve in a straight line. Because we have a number of different planaria and a number of different devices, we decided that a heat map was the best way to visualize the richness of the data that we had, because it gives you an additional dimension compared to otherwise we would have needed lots of different graphs. So we actually started off graphing, and then the biologist says, why don't you use a heat map? And then we went for that approach.
All these things have been done in the clean room?
No,
No.
just normal lab on the bench, just a standard laboratory.
Okay.
Devices are the size of a microscope slide. So we printed the devices in our lab and then took them to our collaborator that's got the zebrafish tank and everything, and we actually did it in his lab.
Okay.
Because that was close to the zebrafish, so we could just take them out of the tank. So with the planarians, again, they sit in the little cylinder. After 15 minutes, they are de-stressed, so we can release them. And then after 30 minutes, you can see them swimming here. They are present close to the chemoattractant. You can see the brown gooey stuff here on what the liver extract actually looks like, which makes it then understandable that if that's around, it is really hard to find these planarians all back. And you can see towards the end of the experiment, the we get a relatively homogeneous solution. So we found an increasing amount of planarians also towards the bottom of the device. So here we've got the heat map of the frequency where they spend on all sides. And we can see that most time was spent for the planarians at the site of the liver extract, which confirmed our hypothesis that the liver extract is a chemoattractant.
How come they are, kindly go to the, how come after 45 minutes they are randomly moving?
Yeah, they're just little swimming creatures. They're little worms that swim.
No, but after 30 minutes they are towards the attractant side, no?
Yeah. So they prefer to swim here. So they go on a random walk. If it smells good, they continue swimming. But then once they've eaten, they may decide to just see if there's anything out there.
Okay.
So they swim all the way around, and at any point in time, most of them are close to the food. But once they've eaten something, they may still think there may be more food somewhere else. So they go on a random walk, and then as soon as they pick up trace, they swim back again.
The right time for detecting is 30 minutes then?
Yes, because after that, as we'd seen...
Can you quantify them that way?
You can just count them.
Okay.
So here we can see, after about 30 minutes, we are halfway. So now you can still say something. If you wait any longer, your chemoattractant will be everywhere, so your results become meaningless.
Okay.
So that worked with the chemoattractants. So we now have understood that we can play with both the resin chemistry and the print parameters to control the porous properties of integrated membranes. If we look at functional integration in 3D printing, however, we have the post-print integration, which is stick a membrane off after, print, pros print. In 2017, we were managed to do some in-print with FDM, fused filament. What we really want to do is do in-print integration of membranes using DLP. So that was the original start of Harry's PhD, to see if we could get there. And indeed, after we had done all this work developing the porous resins, we managed to find a way where we could, without any resin exchange, so without the need for print, pros print, we could actually print a porous membrane inside a microfluidic device. Because what we found is that if we could apply a grayscale mask, so we could dynamically change the intensity of the light during exposure. if we have no grayscale mask, we expose at full intensity, and we optimize the exposure time so that that would allow us to create a dense material. If we then increase the intensity of a grayscale mask, from a grayscale mask of 45 to 75, we have decreased light intensity when we do the polymerization, which means that our polymerization is happening to a less complete state, and we have increased pore size materials. So here you can see with a grayscale of 45, we still get a fairly dense material, but we can still see some pores in there. With a grayscale intensity of 75, we get really, really big micropores. So we initially did quantify that by printing little squares at different grayscale intensities. Here we've got the whole area, and we could see that between grayscale 0 and 75, we could actually print objects. If we went beyond grayscale 75, we wouldn't be able to form any material anymore, and our printed structures would simply wash away. So you can see the digital light projection. You can see the light coming from the LED array. In this type of printer, it's then a phone screen that opens and closes certain pixels to allow the light through. Then we've got the grayscale mask that digitally is applied, so it's a setting that you change in the computer. And then it is similar to changing the intensity of your phone. If you're in a dark environment, you don't want your phone to be really bright. But if you are walking out in the sun, you want to increase the intensity of the phone, because otherwise you can't use it anymore. This is a phone scale as well. So this grayscale tunes the intensity of the light that's coming through. So again, grayscale 0 got a dense material, grayscale 75 we got a highly porous material. And if you look in here, it is because you get increasing amounts of the monomers being incorporated into your polymer structure, where with the 0 time scale there is hardly any through pores there, and we get a more and more open structure being formed by polymerization using the grayscale mask. If we look at the characterization, we can also see that the pore sizes of these materials at a grayscale of 75, we've got a pore size relatively narrow, around 50, whereas with the grayscale, I didn't think we would be very quantitative, but we compared with ICP-MS from the same soil samples, and we were within 2% of the quantitative, the amount of iron established by ICP-MS. So we were quite pleased how well this assay worked. So through this work, I hope that I've demonstrated to you that digital light projection also the integration of materials. We established that by addition of a origin, you can actually change your dense resins printing dense materials to render them porous. There's different parameters that we can play with to tune the porosity of the materials. Some of these parameters are in the resin chemistry. This is the monomer concentration, the porogen concentration, the photoinitiator and the photoabsorber. So in play all those parameters we can tune the porosity, where the photoinitiator allowed for reasonably fine tuning of the porosity, whereas the porogen was our big dial that could get us to an order of magnitude difference in pore size of our materials, as demonstrated with the size mobility trap for the DNA extraction. Printing parameters play a role as well, so we can tune the exposure time, but also with the grayscale mask the intensity of the printer, and other parameters we can use to manipulate the pore size of the printed materials are the layer number, the number of layers that are being printed, as well as the layer height. So this was the functional integration by digital light projection 3D printing. If you've got any questions, then I'd suggest, you've got a question, right?
Not much. A slide before that, where you are talking about the, yes, it is by osmotic, how it is going in that? You have a membrane in between?
Yeah. So
one side you have sample?
Yeah.
And other side it is?
Phenanthrylene solution.
Okay, you are getting a color because of this complex formation.
Yeah.
So, how you are controlling the movement?
It is just wicking. So
Just wicking.
just wicking. So you use the wicking and you start off dry and the reagents from both sides wick in
Okay.
and then they meet each other. And once everything is wetted, transport is by diffusion.
So I was thinking, as if a membrane, it is just osmotic.
Yes, they could be osmotic. So we haven't controlled the osmotic pressure, so there could be osmotic pressure driving fluids as well.
Pore size of the ion moving and the membrane. That are other parameters to be taken care of. No? Pore size of the membrane, you know.
Yeah.
How whether those ions can diffuse through those membrane, that membrane. The size of the ions, pore size of the ions, that will also matter.
Yes, but in this instance, the pore size is a couple of 100 nanometers, so the ion has no problem diffusing through.
Okay.
So the only time that we've worked with the relatively dense membrane was in the size mobility trap, where we ended up smaller than 20 nanometers, and that's when you start being able to select to differentiate between the transport of larger molecules and smaller ones. But these holes are so big that the ion and the phenanthrene had no problem
Okay.
passing through the pores. This is not a small pore size material.
They are vertically placed, or they are vertically placed?
It is printed in 3 dimensions, so it is.
Sir, microfluidic ਉਹਦੇ ਤੇ chamber create ਕੀਤਾ ਹੈ।
What?
नहीं वो
So this is the device looking vertically. So we've got about a millimeter height between the bottom of the reservoir here and the edge. So it goes down.
Okay.
It is like 2 little cups with a barrier sitting in between.
Understood.
Excuse me, ma'am. How the mass affect the pore formation? How the mass affect the pore formation? Pore formation.
Yeah.
How the mass affect the pore formation? When we increase the mass, how pore will be formed?
They are not playing with the mass.
Actually,
Mass किस चीज का?
एक slide में दिखाई थी. We got 0 mass and 75.
Yeah, GS. So
that's the grayscale
just-
mask.
yeah, they are just asking about that.
So
How the grayscale 75 and 0, they are being managed.
yes, so they change the light dose that is given in the light intensity. So if you have a very high light intensity, you get a lot of places where your oligomers, your polymerization nuclei form, because you've got a lot of your photoinitiator that is activated all at once. But if you've got a lower intensity, you've got fewer nucleation sites. So you get a very different formation of your oligomers because your formation rate of your radicals will be different. So we were playing around with the polymerization kinetics by changing the amount of photons that you throw per unit time at the photoinitiator. And
How they are affecting the interaction of the ions? Phenanthrene and iron. They are
they don't know.
Okay.
Iron and phenanthrene are stupid molecules, and they are just introduced into a device that they don't know how it was made. So we first make a device,
Okay.
and then we use it.
Okay.
So iron and phenanthrene just see a membrane as if we had a reservoir with a bit of paper in the middle. They don't know how the membrane was made. They just see something, it's porous.
Okay. Based upon the pore size, just the
Yeah.
detection was done.
So it is just a material.
Okay, sir.
It is just a material that has a pore size that is small enough to stop the dirt. There's my picture. The only reason that we've got a porous material here is that we don't want the soil to be moving into the place where we are detecting.
Okay.
So could we have done this by just clamping a bit of paper? Yes, we could have. But then the device would have needed assembly to put together, whereas this device didn't need any assembly.
When we are using 1 ton phenanthrene, iron 2 is the main Which complexes is it?
Yeah. So the student was not a chemist, so he made up the solution as an iron 3 solution.
Okay.
We had nitric acid present to reduce the iron 3 to iron 2,
Okay.
but the calibration curve, we contemplated changing these concentrations all back to iron 2, but then they become really just slightly different numbers, and we let's just say that we made a calibration curve making up the different solutions at the iron 3 standards. And then we had nitric acid present here to reduce the iron 3 to iron 2, and we made sure that the nitric acid concentration was the same. So he should have made iron 2 solutions and done the calibration that way, but he didn't.
Specified in this case, na,
So
rather
then,
than
for total iron, ascorbic acid or something, so that iron 3 is reduced to iron 2.
Yeah. So the reducing reagent was in there, but he omitted to do a separate calibration where we made up iron 2 solutions, which would have been the thing that he would have needed to do here to make a nicer calibration curve. So
for ICP
good pickup, that was indeed, and yeah, we looked at ways, but we then thought it was most honest to just say we made up the iron 3 solutions and measure the color, because we couldn't, we had no way to confirm that we always had 100% conversion of our iron 3 into iron 2. So we asked him, where is your calibration directly using an iron 2 solution? And he said, huh? I just took the iron and I followed the protocol. So that's when you get an engineer to do a chemistry project.
So, and another thing, ICPAS, you have specifically used iron 3 for ICPAS. You have also
We've used the same sample. So we've used the soil sample that we...
no, standard curve. You must have standard
I
calibration on the basis of which this...
I assume they have done that with iron 2, but it's
Normally for ICP, total iron comes.
I haven't done the ICP-MS. We gave the sample to the department, so we just handed in the sample and we
So
got
I have worked on
that
ICP-MS,
concentration.
that's why I'm saying we normally got total iron. We don't have separate
but it doesn't
iron
matter
to-
because if you reduce all your iron 3 to iron 2, it doesn't matter because you end up measuring total iron
Total
anyway
iron.
if you reduce it all down.
Yes, yes.
Yeah, otherwise, if optical density is measured, then it
Then we can distinguish iron 2, iron 3.
Yeah.
Using
Yeah.
spectrophotometer at a specific wavelength.
Yes, but we don't have the volumes here to do that.
Okay.
So,
Okay. That means
for confirmatory analysis, the lab next door had an ICP-MS and an operator. So we had our soil sample and we just said, you do that and let's see how far we're off, and we're hiding under the table thinking we'd be 20-30% off, and we're really pleased that we ended up with the same numbers. But the paper has got all the detail in there somewhere how the ICP-MS was done, but I honestly wouldn't know.
Okay.
What is the role of 110 phenolphthalein? Means basically, if I say there is a breaking of iron and we are using ICP-MS, ICP-MS will understand the metal ions in all.
They have just verified that binding. ਉਹਨੂੰ verify ਕੀਤਾ ਹੈ, quantify ਕੀਤਾ ਹੈ using ICP-MS.
Yeah. So the
Quantitative
iron testing
analysis.
was just the easiest demonstration you could think of a chemical assay that could benefit from having a membrane barrier inside a reservoir.
Yeah, my question is driving force. If I say it is a braking action or capillary action, then iron is moving from one to the next. Based on equilibrium, it will be setting up certain concentration on the second one. Since you have certain concentration in the sample,
Yeah.
first one, it goes to the second one. Some equilibrium is set up in the second,
Yeah.
based on the initial concentration, and you are able to know using ICP-MS the concentration, what calibration we are making. You have
We have kept, so we haven't considered the drive of concentration gradients, but we have fixed the time to take these photographs in order. So the color intensity would indeed change with time, because you get increased diffusion of your phenolphthalein into your sample reservoir and diffusion of your iron into the other reservoir. So we fixed the time to then
concentration of the iron solution.
Yeah.
You must have taken known concentration of iron solution that you have
Yes,
put
for the
into
calibration
that.
group, yes.
That's what you have verified from ICPAS. That concentration was verified.
The concentration that was verified was the concentration of the unknown in the soil sample.
Ah.
So we got a soil sample, we split it into two parts.
Okay.
One went for the microfluidic
Okay,
testing,
okay.
the other one went to the
Okay,
ICPMS.
okay.
And then we had some other soil that we had on campus that we confirmed with ICPMS that it was the amount of iron present was negligible. So it was under the sensitivity of our assay. So our calibration curve was also made in presence of a soil sample, but one that we knew that didn't contain any iron. So our calibration curve was made with a soil that we know didn't have any iron in there, and our test sample came from a mining site that we knew would be high in iron.
Sir, the question very question. Then specifically unknown sample was taken. Just to verify kita. 110 phenanthroline की concentration vary की होगी sir. बस ਉਹਨੂੰ verify कर लिया.
So our only varied element Okay, stretch our legs before we go to nanoparticle synthesis. I'll give you a little bit of a break. are we? 12:20.
As far as the large upscaling is concerned,
Yes, it can, but it will be an engineering challenge where you may need some feedback loops in control. So it is. It has been demonstrated to go from low microliters a minute to tens of liters. From that point, it becomes upscaling. From there becomes a point of having a big hall and just putting the instruments that can work at 10 liters a minute scale, just having 100 of them sitting next to each other. So is it specialty agriculture? Yes, it will continue to be specialty chemistry. So is this going to be as cheap as getting ammonia-based fertilizer? Probably not, because those processes are so large and cheap. So our nanoparticles will also always be a specialty ingredient that therefore will be more expensive because it requires a more advanced manufacturing method. But your bulk synthesized nanoparticles will have exactly the same effect because they need very advanced stirring that isn't as scalable as just the crystallization of ammonia for fertilization either.
yeah, as we normally use probe sonicator and all, or micro, what other tools we are having for creating nanoparticles, all those are too much expensive. Even probe sonicators and all,
Yeah.
when they are to be used on a very large scale, so
So I think going in parallel, you'll have fewer issues than just going for trying to sanitize a swimming pool.
yeah,
But you will need to have a hall the size of a swimming pool where you've got 1,000 different machines operating in parallel. And I think there will be probably a curve where nanoparticle synthesis in bulk would be cheaper at a certain size scale, and using a microreactor, there will be another scale where it's cheaper. So I think the cost points in each and the pain points of scalability will sit somewhere else,
okay,
and it will depend on how monodispersed do you need to have
yeah.
it, how pure are your reagents that you want to feed in.
The biggest advantage I could see from this, your presentation was the monodispersity.
So
That
maybe agriculture is not the right application there because maybe it doesn't need that level of monodispersity. But if you use nanoparticles for drug delivery or for making optophotonics, then your bulk methods are insufficient. So it depends on what the economic picture is.
And how the thickness of channel affect the mixing? Suppose
The smaller the channel, the better it mixes, because the lower your distances for diffusion.
suppose we use a grain synthesis method in nanoparticle synthesis. So we have an extract of some plants.
Yeah.
So can we use these channels for the mixing of or incorporation of metal in
I think so. I would just not start off with really small channels. I would go 200-300 microns and just see what happens. You may need a higher higher flow rate to achieve the same effects because you want to increase your Reynolds numbers to take advantage of these mixing effects. So you may need an HPLC pump or so to work with it. But if you even have some 0.5 millimeter bore tubing hanging around in some T-pieces and connect it up with an HPLC pump, I think you'd be...
And suppose we can, in grain synthesis, suppose we can incorporate zinc in plant extract. So we can produce zinc oxide nanoparticles. So which concentration is good for the mixing? And suppose we can use zinc sulfate.
I don't know. So that would be a matter of looking at literature, what concentrations have been used. the first day you do it, you go half and you go double, and see what happens.
In my department, a lot of students are working on green synthesis of nanoparticles. They use very small concentration, like I think 1/1000 molar concentration.
Yeah, that matches with one of the papers that we talked about that showed that you got better monodispersity and smaller particle size, the lower the concentration. So you don't, I think you want to limit the number of nucleation sites so that you don't get too much coalescence taking place. So you pretty much want to have a low concentration to allow each nanoparticle to form itself, and not to be having too much interference of what's happening in the neighboring nanoparticles. And I think that's the reason that the low concentrations typically work better, because you limit the interference between different nucleation sites.
When we produce in upscale the nanoparticles in upscale, so which kind of problems we have faced in the production of nanoparticles in upscale?
Having the pumps that deliver the flow, getting rid of the heat that the pumps will generate, because if you need to get a room full of high pressure pumps, you'll need to get rid of that temperature effect. And I think you'll have some practical issues making sure your tubings don't leak. So make sure you use good fittings. I'd probably go for screw-on fittings rather than pull-on, because if you get a little bit of pressure things pop open. So I think your plumbing, heat generation and plumbing is probably, and that they are, if you go to really industrial scale, there will also be industrial solutions that have been developed to dissipate heat. Just have each pump equipped with a large fan.
Thank you.
So I think our role as chemists is to get it kind of to the liter scale.
Okay.
And from that point, it is chemical engineers that
Yeah.
will have to use their experience
For
in
upscaling.
how you upscale the industrial processes. How do you have big pumps? How do you get the control systems? And there will be a little bit of change thinking that it may be better to have multiple parallel modules rather than to increase the diameter of all the tubing. But yeah, there will be space. But I think practically balancing 5 or 6 different fluidic lines I can do leak free. If I go beyond that, there's always one way the fitting isn't quite right, or you haven't put them perfectly plumbed together, so there's a slight angle, and then you increase the pressure and you get your first leak. So there will be, make sure that your lab doesn't heat up by your pumps too much if you use them at really high power, and plumbing leaks. Or have so much tubing there that all of a sudden there is the tubings end up in a knot, and one of them forms a flow constrictor, because then all of a sudden your back pressure increases and then your fitting pop. So you've got a nice bundle of all your tubing, then something changes and one clamps on the other. You've got a flow resistor that you were not planning on, and then you've got reagents squirting everywhere.
Thank you.
So let's then have a similar bird's eye view on agricultural applications of different microfluidic devices. And in food and agricultural industries, microfluidics can be used for food safety, food processing, animal and also plant sciences. So there's a whole range of different challenges and problems in food and agricultural industries that can be addressed using microfluidic solutions. I found one nice example of a recent article where at IIT Guwahati, not sure if I pronounced it right, they looked at some microfluidics to understand the development of plant roots. And that shows very nicely that microfluidics can be used for the fundamental understanding of plant and pathogen interactions. As that article that we're talking about, it gives understanding on how pressure and flow can change, morphological changes in developing root systems. Microfluidics can be used to understand the uptake of nutrients by plants, but also the transport of nutrients within soil. It can be used for the detection of pathogens, either through PCR or through metabolites that are characteristics for the presence of these pathogens. And then the metabolites, the biomarkers, can be both derived from the pathogen but also from the stress response by the plant. And it can be used for the detection in pesticides to make sure that us as consumers are not eating too much pesticides when we eat some tomatoes. There's probably many more applications, but these were a couple that I could think of on top of my head. So here we've got a device created by the group at IIT. You can see a microfluidic structure here, made probably out of some PMMA plates, where they had little cradles to place seeds in parallel, and they were able to have these seeds germinate, put them in a nutrient solution, and then look at the development of the growth of the plant root. And with this work, you can see that this in here is a flow cell. So we've got a tubing connector coming in, and we've got a fluidic connector here, each cell coming out. So we have control of the flow rate plus this growing root. And what they realized is that whilst the diameter of these roots stayed the same, the thickness of the cells here in the middle changed depending on the flow condition. So here we've got some diagrams that show how the microfluidic was being used. We talked about parallel processing, so here we've got 7 or 8 different cells sitting in parallel. Here we've got the way that you use only once. So we've got the plant inlet here. We got the seed or the just germinated seed. We can introduce. Is that a speaker? Something doesn't sound quite happy there. So a little cavity here where we can put a germinating seed in, and then a flow channel to pump by the nutrients, but most importantly for this set of experiments, change the flow rate that these nutrients go by, because that changes the pressure that's applied to the developing root. And what they were studying in this work was to see how that changed the root morphology. So here we can see that the little plant was germinating, growing, and the root would slowly find itself a way down the microchannel. Here you can see that with different flow rates, the length of the root changed, but there was an optimum at 0.4 microliters per minute. It was a relatively long root being formed, but beyond that maximum flow rate, actually the root length became shorter again. So here we can see the quantitative analysis that was done on this developing root, where at different time points the root length was measured for the different flow rates. And over the different intervals we could see that, so here are the lower flow rates, here are the higher flow rates, and we can see, as we already could see on the diagram here, there is an optimum where we get the longest roots being formed, after which the length of the roots gets smaller again. So here we've got an upwards trend with flow rate, here we've got a downwards trend with flow rate. After taking these roots out of the microfluidic devices and studying them, it became obvious that if we increase the flow rate, the number of cells separating the core of the root from the shell actually reduced. So at a low flow rate we had a relatively large space here, and this area, the thickness of this area changed depending on the flow rate. And here we've got a way of looking at the pressure that is being applied. So the loading flow we can calculate with the flow rate, what actually the pressure is that is applied to this plant root at the interface. And we can then dissect the roots. We can see that the size of the roots, the outer diameter, actually didn't change with the flow rate. So we, as a result of the different flow conditions, this research found that whereas the exterior of the roots looked very similar in diameter, the cell differentiation inside these structures was very different, and we got changes in the core to a phloem ratio depending on what the pressures were that were applied to the outside of the root. And that's something no one had ever seen before. There have been no other tools where we can apply a continuous pressure to a developing plant root to actually look at the morphological changes of the different cell types, the differentiation of the different cell types inside a system, and then take them out and allow them for analysis by microscopy. So the changes in cell differentiation and therefore the morphology of root as a result of different pressures is called thiomorphogenesis, and this was studied in using a microfluidic device. The important findings coming out of this research was that increasing flow rates boost the root length and the nitrogen uptake until reaching an optimum flow rate. At too high a flow rates, there's clear stress on the cells, and the roots don't get any longer. Moreover, due to the high stress, they get even shorter. They get shorter again. The roots in the flow traditionally consistently outperformed those in no flow conditions. They grew faster because they were able to take more nutrients out of the flow because there was more nitrogen flowing by. And nutrient flow induces the morphological changes, offering new insights in root adaptation and cellular responses to changes to the physical environments. So very simple microfluidic device, but by understanding the fluidic properties, by understanding how a flow changes the pressure, a whole range of new experiments could be developed. After the experiments, the roots could be taken out of the device and characterized using microscopy, leading to new biological understanding, which in turn potentially can be used for hydroponic culture, and understanding how to optimize flow rates in hydroponic culture in order to get better crops, get good, strong root development, but not to get to the flow rates that get to too high a shear stress that again then lead to decreased root development. So using microfluidics can be used in agriculture to get new understanding, to then enhance the microscale phenomena again. Looking at other option is to look in a closer detail at nutrient uptake. And here we've got a microfluidic device where again the developing plant can be studied. And what this device has is that it's got two embedded electrochemical sensors. One of these sensors has got a functional layer that it measures phosphate. The other one measures nitrate from memory. And can the picture in the set of slides that you get, the picture is a little bit better than here on the screen. But we've got a little fluidic flow cell here with 2 different nutrient sensors, each selectively measuring one analyte. So over time we get time-based profiles for 2 different analytes. And we've got a little cradle here to a little germination pot where we can add the legume seed that is with growth going to be consuming more of the nutrients that we can then monitor. So this is the way that the different electrochemical cells were created, where we've got a working electrode, a reference electrode, and they were functionalized with materials to create selective electrodes for nitrate and phosphate detection. So here we've got the 2 different electrochemical sensors. We've got the little seed being placed there. The seed develops a root and starts taking up nutrients out of this containment. We can see that the distance here, the different measurements are being taken on different days. And we can see a very quick decline in our nitrogen concentration compared to the phosphate. At day 5, we get fresh solution being introduced. But we can see that the slope here in the nitrogen uptake has increased compared to the early time, which is not a weird observation because we've got a much larger plant after that 5 days, and therefore we've got a larger metabolic capacity, which correlates with a larger capacity to take up nitrogen. So this allows, in this instance, it was made for 2 obvious nutrients, nitrate and phosphate, each having their different rate of uptake. But by changing the chemistry at the sensor head, you could change the nutrients that you're looking at. And you could, for example, start studying the role of certain micronutrients at the development of stronger root systems, or the rate at which we start getting to the 2-leaf, 4-leaf stage. So by being able to monitor the nutrient uptake, we actually know as a unit of time at what point in time the developing plants need what nutrient profile. So another part in agriculture is not necessarily looking at the development of plants themselves, but look at the development of disease. And this article here is the microfluidic platform that was used to study microbial spore germination under different conditions. Here we've got some picture of the microfluidic device, and there's 2 fluidic features that are important where we take advantage of microfluidics and miniaturization. The first thing is that because our microfluidics allows fine scale control, it allows us for the loading and the distribution of different bacterial species into a device and study them individually. So we can create little reservoirs, little cavities, where each of these spores can be individually placed, and using a microscope we can monitor the germination of multiple spores in parallel. But we don't look at an overall spore development, we don't look at averages, we can look at the development and germination of individual spores. The other microfluidic feature we can use is the fact that we have laminar flow. Because if we've got laminar flow, we can create and control concentration gradients. Here on the right-hand side, we can see that we have some high concentration fluid coming in at this side, some low concentration of our inlet coming in, and we can see a stepwise increase of our chemical, in this case fluorescein, because it makes it nice and easy to visualize, and that will continue through our flow cell. So if we have our little tray loaded full with spores, so every spore has got its own little cage to be sitting in, we then know that all the spores that are sitting in this area are not exposed to a certain reagent. All the ones that are sitting here are at about a quarter concentration, 50, 75%, 100% of concentration. So we have a concentration gradient, and we can conduct cell-based studies on individual spores under a range of different experimental conditions without having to really do anything. There's a microfluidic structure that allows you to make this concentration gradient. So you just introduce water and your reagent that you're looking at. the fluidics will take care of the fact that we get this gradient formed. This gradient will flow over these different bacterial spores, and we can, using a microscope, monitor them individually, do large-scale image analysis, and do a number of experiments that usually would have taken weeks in the lab in a few days by just doing them in parallel. Here we can see one example where we see the germination of one of those spores with Bacillus subtilis, and you can see that over a 2.5 hour period you can actually see the morphological changes as a result. So what they did...
Can you go to the back slide? I couldn't get that how the microfluidic device is giving us the
it is an area where you split the flow and split the flow again. So if you've got 100% water and 100% fluorescing coming together, and you then split the flow in two, then you get 50-50 concentration. If you then add more water coming in, I'll share another paper. So you can use the flow resistances of different networks to have different mixers and create a fluidic gradient using flow resistance. I'll show you one of the devices. That it's one of the things that's impossible to explain. And once you see it happen, it works like a Christmas tree. So it branches out.
Okay.
You get different ratios of water and dye being mixed.
You haven't got your box yet?
No.
Oh.
Otherwise I would have shown it here. So here we've got the germination rate at a nutrient broth, synthetic media, and L and D alanine. And what they looked at was the germination of the different seeds. You can see that in the nutrient broth we got very quick and good germination. L-alanine was clearly important there because we still get, when only alanine was there, we can get good germination. If we get D-alanine, there is no seeds germinating, so that's not good for the development of bacteria, or excellent if we don't want the germination to take place of these bacteria. And if we look at the synthetic media, looking here at 46 different in parallel, they just don't germinate. So there was some statistical analysis being done on how the concentration of the alanine affected the germination rate, realizing that you got really good germination at a higher concentration, and at a lower we actually had a reasonable fraction of them not germinating. No significant differences were observed between the 1 molar and the 100 micromolar, but the spread for the 1 molar, the spread in germination rates was slightly higher, and therefore the 100 micromolar was picked as the optimum to get synchronized and fast germination of these microbes. So here you can see a little movie where you can see the morphological changes happening over time of one of the bacteria that was studied. And this is again this is done with a microscope and with so many different experiments happening with microscopy. Image analysis actually allows you to track things based on location and time, and then you can quite quickly analyze the data and see what's happening. So here again we've got concentration changes of one of the other reagents. Yes, so it's indeed not the reagent. It's the it is different concentrations. I just don't know what reagent it is, and it's not here in the notes so as well. But again, we can see that we've got changes in germination time depending on the concentration. And at the highest concentration we got no germination at all. So our optimum condition, if you wanted to have germination, was to be at the lower concentration range. So the reason for putting this in, it shows that you can actually look at individual bacteria. If your problem with bacterial formation is that you don't want the spores to germinate, this allows you to test a whole range of chemical conditions where you do or you don't get germination. Which provides you a very good starting point of working with selecting chemical conditions that you can prevent the germination of these bacteria, unless they're ones that are used for fermentation processes. So if you want to promote, you can also select those conditions. So early detections of threats and disease is one of the parts that I like to work at. And of course, in agriculture, there's a whole range of different microorganisms, bacteria, fungi, viruses. There's a whole range of different microorganisms that can affect the quality of vegetables, fruits and grains. And recently there was a really nice review on how microfluidics has helped with the advancing the early detection and the on-site detection of all these nasties in the agricultural sector. One of the ways that can be helped is using Internet of Things. So have little microfabricated devices in there with a sensor that will be able to give you a reading that transposes on your phone. So you actually don't need to be on site to do the monitoring. So they made a device using a dry film photoresist. They used photolithography, so they used a mask to selectively make part of that photoresist soluble, part of that photoresist insoluble, and create a fluidic structure that way. This allowed them to make a negative mold, to then cast the PDMS over to create microfluidic channels. And they then sealed the microfluidic channels together onto a glass slide to go from an open channel to a closed fluidic device. What they also did here was to cut a little hole in an acrylic device, because in the ultimate device they wanted to have a little reservoir where they could do spectrophotometric measurements. The whole device was relying on having your sample coming in with the reagents, having a microfluidic mixer to allow the target analyte to actually react with the reagent, and then measure the absorption by putting an LED with a fixed wavelength on one side of the detection chamber, a photodiode to the other side, then use an impedance amplifier, a single board computer, in order to either through Bluetooth transmit the signal to a laptop or a phone, or to use an Internet of Things module to directly get the data stored in the cloud, so that people could, from a very different location, understand what in this case, the nitrate concentrations were. With the reagent, the method was validated that there was an increase in absorbance with the increase in concentration of a target analyte from 1 molar to 1 micromolar to 30 micromolar, and it was also confirmed that with increasing concentration, the detection voltage coming out of the photodetector decreased. The change in signal could be correlated to the concentration present, and therefore the system could be used for the monitoring of the nitrate. This is some of the work that we've done probably 10-15 years ago to see if we could decrease the sample preparations of fruits and vegetables for mineral analysis. We had a project, and the students, we really were struggling to get bits of fruit chopped up, see if we had to freeze them, grind them with a mortar or pestle. And our question is, do we have to go through all this work, or could we just be lazy? And could we put a bit of fruit in our analytical instrument and inject our analytes? So here we've got a bit of zucchini being stuck in a sample vial. In this instance, it was a capillary electrophoresis instrument, but it's exactly the same types of vials that you load into an autosampler for a gas chromatography instrument or for an HPLC. We found to our great delight that indeed we got a nice profile, nice separation of our inorganic cations when we injected directly from a bit of zucchini, but we had horrendous repeatability. We had no consistency if we had a bit of the same zucchini. We got very different results, and initially we blamed biological variability, because that's always a good one to blame. But we thought that was a little bit too easy, and we then decided or realized it was actually not biological variability, it was fluidics taking place. Different plant cells carry different amounts of water, and that actually applies a fair bit of pressure. So if you poke a few silica capillary, glass capillary into glass, Sometimes you're in the interstitial space, sometimes you are in a cell itself. The pressure that's being applied is actually different every injection. If you apply a different pressure, as microfluidics people, we should have understood this, different pressure means different volume. This means that if you randomly poke a capillary into a bit of zucchini, sometimes you are in an area where you've got high pressure, sometimes in your area that you've got low pressure. You inject different volumes, which means that your calibration curve doesn't work anymore. We decided to fight back, and we're like, how can you fight back against pressure? You just want to apply more pressure from the other end. We didn't quite want to apply mechanical pressure, but we introduced the viscous reagents. Viscosity increases the back pressure, which means that by increasing the viscosity inside our capillary, the differences in pressure from where we injected the capillary into the zucchini actually didn't matter anymore. So increasing the viscosity means that we needed a much higher pressure to get a significant variability in volume introduced in our capillary, which means that we stopped the zucchini's ability from squirting liquid into our fused silica capillary by just having a highly viscous solution in there. If you then apply a potential difference, you are doing a purely electrokinetic injection, which then means that you get good repeatability. And as you can see here, we've done the analysis of potassium, calcium, magnesium in zucchini, apple, and mushroom. We also did tomato, strawberry. We've just got the whole vegetable shop and just put them all in different vials. We got the separation to work the same way. And we confirmed the analytical answers that we got out of our capillary electrophoresis method with ICP-MS. And we got a good correlation between the two different results. So we could cut down a significant amount of sample preparation here by directly injecting our analytes from the fruit. We could only do this with some understanding of the fluidics, because when you put the capillary directly in the fruit, the pressure, depending on where you end up in the cellular structure, the liquid pressure generated from there is very different. So with an aqueous electrolyte, without any viscous reagents, the pressure differences between the different locations in the fruit made a significant contribution, and therefore we had poor repeatability. But if we increased the viscosity, the pressure changes became negligible because they couldn't overcome the back pressure of the liquid inside our fused silica capillary anymore, and we could get consistent results. Another example of applications in agriculture is to look at the detection of fungal infection biomarkers. In this instance, there are three different fungi, I think they were. Three different pathogens that could affect grapes. And if the grapes were being impacted, there were increased concentration of jasmonic acid, azelaic acid, and salicylic acid present. So the idea was to develop a device that these three different biomarkers for fungal infection could be detected at the same site, at the same time. So here we've got the microfluidic device that was again integrated into a system onto a printed circuit board, but here we've got the fluidic device itself, where we have one side where we can introduce the sample, and we've got three different analytical zones where different nanoparticles were created to conduct three different assays. So we've got one sample coming in, we've got three different areas where three different assays can be taken in parallel, and then using the photometric results, we can quantify the concentration of these three different biomarkers, and with this assess if our grapes have been affected by one of these fungi or not. The first reagent that was used were some functionalized titanium dioxide nanoparticles that leaded in presence of the salicylic acid they led to some agglomeration, whereas in absence they didn't. And we could get a linear concentration of the optical signal based on the presence of the absence of the analyte. The second assay taking place was the conversion of, was an enzymatic assay that was being conducted. So there was some tyrosinase and its substrate, and in presence of our biomarker, so in absence of the biomarker, the enzyme would convert all the substrate, whereas in presence of the biomarker, we got inhibition of the enzyme, and therefore we got an increased presence of the substrate, which then could be connected with our enzyme-based assay. And again, good linearity of the concentration of the biomarker relative to the response. In the first instance, we've got an ELISA, an immunoassay, where we get the binding of our biomarker to protein and then to an antibody for detection. So again, in absence, we have no binding of our biomarker to the BSA and therefore to our antibody, and we have no signal, whereas in presence of our analyte, we do get our sandwich assay to work, and a complete ELISA assay could be conducted for this biomarker. So in this article, the 3 different assays are validated, and it allowed for multiplex detection of the 3 different biomarkers through the development of 3 separate selective assays. This in here is a work where we used a pumpless acoustofluidic device for rapid detection of pathogens in fruit. And again, we've seen this device come by past. What we used was very quick mixing of these acoustic micromixes by having the triangular structures next to a bubble, creating these curvature flows that we've just already seen come by with the nanoparticle synthesis. In this instance, the micromixes were used to homogenize the fruit mixture with the lysine solution. Then there was a filtering functionality at the end to stop any cellular debris, and we could, with a pipette tip, isolate the clean sample from the other side. The liquid flow, the fluidic flow in this microfluidic device was driven by a highly wicking fiber, so we didn't need any external pumps that needed electricity. We just put a highly hydrophilic fiber that we extracted from nappies. We put them at the outlet of the microfluidic device. They wicked up the liquid, acting as a pump, drawing new liquid through our micromixer. The little speaker that we'd extracted from a speaker that we bought in a cheap shop. A speaker allowed for the quick mixing, and the thread-based device here allowed for pulling the liquid of the heterogeneous strawberry or raspberry extract from one side to make it homogeneous at the other and ready for amplification of the DNA. So we looked at the mixing efficiency under different frequencies, and we could find an increase in DNA copy number by PCR if we spiked more E. coli onto the fruit at the start of the assay. So we started off with a piece of raspberry, mimicked the contamination by depositing a known amount of E. coli, and we could indeed use the homogenize the fruit as well as mix the fruit and the bacterial sample with lytic reagents, use the thread to drive the liquid through the microfluidic device, and then the inbuilt filter stopped all the cell debris from coming to the outlet, and then we pipetted that sample into the PCR and amplified the DNA in order to allow us to quantify the number of DNA that we found back on the sample. The last device I think I want to talk about is a simple paper-based device for the detection of some parathyroid in environmental water samples. So that is, the parathyroids are a group of pesticides that are frequently used in agriculture, but you probably don't want to have on your tomatoes. A colorimetric reaction that was selected for these reagents was developed. With that came a microfluidic device. If you remember us playing in the lab with the paper microfluidics, paper microfluidics allowed us for the creation of hydrophobic barriers where the aqueous solutions and reagents didn't want to go, and leave some hydrophilic patches where we could transport our reagents and add our chemistries. So here we have some paper impregnated with paraffin oil, so acting as a hydrophobic barrier other than in the areas where we're open. We've got a nihedrin layer where little discs soaked in reagents. We've got a buffer PVP layer where we've got little discs with that reagent. On top we've got a laminating pouch that's transparent but has some excess hole to deposit the reagents. All the way on the bottom of this device we have a transparent film that is not allowing any of our aqueous reagents to go through, but provides a leakage tight barrier so that the reaction can actually take place. If this is all put together, we've got a sandwiched device that's got a water impermeable bottom. It's got some reservoirs defined by using hydrophobic barriers. It's got discs that provide different reagents, and it's got excess hull that we can pipette different samples into. And indeed, we selected the coulometric reaction to be in there, and depending on the concentration of each of our 4 target pesticides, we got an increase in color intensity of the coulometric reaction on the paper with increasing concentration. And luckily, with other known pesticides that were not part of this class, this coulometric reaction didn't take place. So we could quantify based on the change in color. The people here were able to quantify the amount of this class of pesticides present, knowing that the other commonly used pesticides could not be detected by the same assay. So that wasn't the last one. This is one looking at acetylcholine esterase inhibitors. Again, very good pesticides. Not very good if you're a farmer, you're exposed to them, because then most of your own pharmacology doesn't really work anymore. Here we've got a droplet-based reaction system where we've got the acetylcholine esterase, which is an enzyme that's present in our bodies for the breakdown of neurotransmitters. In this instance, we wanted to know the presence of inhibitors to this enzyme because they are toxic for our bodies but also toxic for some pests, so they're frequently used as pesticides on the farm. If we've got the inhibitor absent, our acetylcholine esterase happily converts acetylcholine into its esters, which can then be oxidized and measured electrochemically. If we've got an inhibitor present, we inhibit the activity of this enzyme, which means that we lower the activity of our acetylcholine esterase. We've got less of our thiacholine being formed, which means that we got less of our oxidation reaction, which means with an electrochemical reactor, we get a lower signal. In this instance, the assay was conducted into little droplets. So here we've got oil as our continuous phase. We get our aqueous reagents, which are our enzyme, our substrate, and our sample to come together in a little self-contained system in our microfluidic droplets. Mixing will take place automatically because we get the circulatory movement happening inside our droplets. Then our enzyme can get to work. If our enzyme is working fine, we get a high signal from the electrochemical detector. So you can see the working and the counter electrode being introduced here with the reference sitting elsewhere. So we get a nice high signal if our enzyme activity is high. However, if we had an inhibitor present in our sample, we get a decrease of signal measured by our on-chip electrochemical detector. Here we can see some electrochemical characterization of our detectors, and we can see that we can get an increased detection signal with an increase in analyte. And here we can see our droplet passing by our detector. If both of our detection electrodes are in contact in our aqueous droplets, we get electrochemical conversion. If we're back into the oil phase coming by, we get no electrochemical conversion. So we can see each of our droplets coming by because our electrochemical detector only provides a signal if it is in contact with the electrochemically active species. using the flow ratio, so you can see that we had the 3 different channels here. Using the flow ratios between our substrate and our enzyme concentration, we can add different amounts of substrate. So here you can see changes in pink color, pink intensity in our droplets. So we can potentially change our substrate concentration to do more advanced enzyme kinetic assays in the device. And here we can see a series of droplets coming by. If an inhibitor is injected, we can see that if there's no inhibitor present yet, we get high currents because we get a high signal from our electrochemical conversion. If we have a high concentration of an inhibitor present, our esterase doesn't work anymore. We can't do our electrochemical conversion. And if we stop introducing our inhibitor, our signal recovers, and we can understand how much of our inhibitor we had present based on how much our signal intensity drops here between having no inhibitor present and having our inhibitor there. So you can see here in the lower signal, we've got more signal left than we had under A. So as a summary, in agriculture, it's a big field. There's many applications. Some of the applications study the biological processes, which could be optimizing nutrients. It could also be looking at how different force fields affect plant roots. We've got analytical applications, which could be detecting nutrient uptake, optimized nutrient profiles. It could be detecting pests, as well as the pesticides to ensure the safety of consumption of the reagents. Additionally, we can create nanoparticles for agriculture production that then facilitate growth. That would be an application in agriculture as well. I just saw my phone buzzing that it's time to go for lunch, so I'd suggest we start 15 minutes later as well. It's time to go and eat something, and I'll see you back for 1 hour of lectures and 1 hour of a little bit of an idea how we'll do the exam later on. Thank you very much for being patient.
Must have tired as well.